Hi everyone, my name is Usman Khan. I'm a professor of electrical and computer engineering at Tufts in USA. Um, and before I formally proceed with the webinar, of course, I would like to welcome everyone to our webinar, and I would like to thank you for your interest in this special issue. And I hope that after this webinar, you learn something that it is of some value. And before I formally start the webinar, I also want to take a few moments uh, to 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 share the rationale of this special issue. So basically, this special issue brings together subject area experts from three different disciplines: signal processing, control theory, and machine learning. And when we started planning this webinar, we felt that even though these three areas and the scientific community in general is addressing very similar problems, but there is still a language kind of a divide. We think about problems in a different way, but use the same tools to address these problems. And we wanted to showcase these different research paradigms and show that there is an underlying theme behind it, which we call optimization tools and methods for data-driven learning and control. So with this thought in mind, we invited several uh, researchers, very well-known researchers from the areas of signal processing, control theory, and machine learning. And I hope that you would find the set of articles presented in this special issue to be of interest and to be of value. So let's proceed. And my goal here would be to give a quick introduction of the problems of interest. What is data-driven learning? What is data-driven control? And how does optimization theory, what role does it play? And how does it kind of lead to solutions to these problems. And then I would have my co-guest editors, Professor Wahid Bajwa from Rutgers and Professor Mike Rabat from Facebook, to discuss several aspects of the topics that we have covered in this special issue. So um, I would also like to thank my guest editors, Wahid Bajwa, Angelia Nedich, Mike Rabat, Ali Sayed. I'm hoping almost all of them are here. But without their help, without their effort, we would not be able to have a successful special issue. So what is learning from data? So here, um, in general, we have seen recently that data has exploded. There is data everywhere. There are we would view data-driven problems from a very traditional standpoint. In the past, for example, we know about image classification problems where you want to classify all images of dogs versus all images of cats. But more recently, we have seen that data-driven techniques, data-driven learning has propped up in many aspects of society, which we couldn't think of several years ago. So, for example, we know that in advertising, data is being used. We know that in political campaigns, actually, social media feeds and similar data-driven learning techniques are being used. So for this, in this special issue, we would like to focus on these data-driven learning problems with a particular emphasis on where the research is currently, where the research is going in future, uh, and and we want to drive all of this with the help of modern applications. Uh, so let's consider a simple example. So in this example, so think of a self-driving car, and the goal for the self-driving car is to recognize traffic signs, right? So in a very simple case, we want to distinguish between two classes of images. One is all images of stop signs, and the other is all images, let's say, yield signs. And these images, what I show in the top left figure, these images can be thought of as points in a high-dimensional space, such that I'm showing all of the stop signs as stars and all of the yield signs as triangles. And given this collection of images, so we assume that this is the training phase, so the labels are known, so we know which image belongs to which class. We would like to learn a classifier. So a classifier here is a straight line in my top left figure, but a hyperplane in general that separates these two classes such that when a new image comes in, I'm able to predict which class that image belongs to with the help of this classifier. So the underlying problem for formulation goes like this. So we have given labeled data. We have a collection of images. I'm calling them Z's. and we know their labels. I'm calling their label y's. Given a hyperplane, a model, or a line in this top left figure, which I'm defining or denoting as x, we predict a label for each image, right? So given x, you can see that given the red classifier, let's say, I'm able to predict several blue stars correctly, but there are three triangles that are misclassified, and there are three red stars that are misclassified. So I can give this classifier a score. So the score here would be 6, right? And now, with respect to the green classifier, you can see that all the red points are misclassified, but in addition, there is a green triangle that is also misclassified, right? Uh, so the score of this green hyperplane or classifier would be 7. And I would like to find the classifier which has the minimum kind of this error, or that minimizes the score, right? And that I call X star. So mathematically, I have a minimization problem at hand where I take my image Z, I take my sum classifier X, I predict the label. This prediction is given by this function G, and then I compare this prediction with the true label Y with respect to some loss function, right? And this loss, you can think of this as, okay, this could be a squared error loss, but square error is a nice loss function. It could be absolute error. It could be something which is more kind of sophisticated than just a squared error. But in the end, we have a loss function at hand, and we can view and we can easily see that different predictions. So in the previous slide, the prediction was a linear classifier, and different loss functions. So there could be a logistic loss or a squared loss would lead to different functions that we want to minimize. Um, so what optimization theory and methods allow us to do is they give us the tools to minimize functions. And it turns out that when we impose different qualities and different functions, then the underlying optimization method that we use has certain properties, certain aspects, certain behavior that we want to study. So, for instance, in certain optimal control and signal estimation problems, we have often seen quadratic loss functions, which are just expected squared errors, mean squared errors. In logistic regression, for those of you who are familiar, the loss function is convex, um, but still smooth. But if you think about support vector machines, the loss functions are convex but not smooth. And if you think about neural networks, things kind of become, a little wild, where the functions are non-convex, potentially non-smooth. And I was able to find some examples from Wikipedia just to demonstrate how the geometry of these loss functions look like. So for instance, the second figure here is what we call an egg holder function. And you can see this is highly non-convex. It has a lot of local minima. It has a global minimum, I believe. And this function is still smooth. Loosely speaking, by that I mean that it's differentiable. But on the other hand, the third figure in the top, this loss function is again non-convex, and you can see that it has certain discontinuities, and not really but it's not smooth, right? And if we want to minimize functions which are non-convex, potentially non-smooth, then you can see that gradient-based approaches or subgradient-based approaches would run into several difficulties. When we think about functions which are vector valued in higher dimensions, we have issues of saddle points. We have issues of whether the function is differentiable or not. We have the issue if we are close to a saddle point, then how fast we can escape the saddle point. Do we converge to a local minimum or a global minimum? And these issues are magnified when we think about neural networks, for example. So optimization theory is to develop and methods is to develop fast, efficient, robust algorithms to minimize different types of functions that belong to different function classes. And here by fast, I mean convergence speed. So we want our machine learning algorithm or learning algorithm to learn fast. By efficient, I mean computationally efficient. So we want that the computations required are not too expensive. They are not intractable. And by robust, I mean that the algorithm is robust to imperfection. And imperfections could arise in, for example, when data has noise or when the function is not clearly defined, etc. Another aspect of optimization theory and methods is this process of data collection. So we want to know, for instance, we want to, under what, like how do we collect data? And there are several different scenarios, and two important scenarios that are being considered in research are these batch data versus data collected in real time. So this is how we can think about it. So batch data is, for example, suppose that we are given a collection of 100,000 images that belongs to two classes or several classes, and you want to learn a classifier that places that puts these different images in different classes. So in this case, the data, since it's already given to us, we call it batch data. But you can easily imagine that in a scenario where data is not stored in a hard drive, but data is measured or collected in real time. And then the next issue is that when we collect data, um, is does that data lead to a clean kind of a measurement or a measurement with noise? So for example, and this is where we have this concept of an oracle. So an oracle could be something where you query the oracle with a point x in some space, and the oracle resolves the function value at that point, f of x. This is what we called a zeroth order oracle. The oracle could return the first derivative or gradient, more generally, of this function, which we call the first order oracle, or a second order oracle, which returns the Hessian matrix. And then the oracle becomes stochastic if these things are returned with noise, or they are not stochastic, these are returned perfectly. And you can immediately see that optimization problems, which will use a first order oracle, right, would be different than optimization problems which would use a stochastic first order oracle, because that leads to stochastic optimization, stochastic gradient descent, stochastic quasi-Newton methods, for example. So in this special issue, we have come up with a collection of articles which we believe are important, first of all, and also which are diverse enough that they provide a good comprehensive view of the field. So for instance, we cover several theoretical aspects. We cover fundamental optimization methods, as in zeroth order, first order, second order methods. We cover stochastic methods, distributed problems, which Wahid, my co-presenter, would describe. We covered non-convex problems. We covered accelerated solutions, where we come up with optimization algorithms that converge even faster than their kind of. And then there is an article on variance reduction, which is a more recent technique on um, showing acceleration for stochastic problems. We show um, these theoretical aspects with the help of several modern data-driven applications. So we have um, an application considered which is on adversarial attacks in deep learning models. We have applications which show advertisements in search engine queries. We have distributed energy trading. We have robotic swarms, etc. Um, and from a bird's eye point of view, this special issue has 12 articles and co-authored together by 13 different authors representing 11 countries. And I think this is something that we are certainly very proud of, that we were able to get researchers from um, you know, many different regions. But again, this list is still not exhaustive, and our goal was to cover as much diversity as possible without compromising the coverage of the topics. Um, and before I open the floor for my co-presenters, I would like to express my gratitude to the Proceedings of the IEEE staff, especially the EIC, Professor Gianluca Seri, Vaishali, who introduced me, Joe Sun. Without their help, we would not be able to be here. And the feedback that we received from the Proceedings of the IEEE editorial board, and of course, all of our esteemed colleagues who contributed their research and worked with us tirelessly in producing the high quality papers that are a part of this special issue. So the rest of the webinar, the next speaker will be Professor Wahid Bajwa from Rutgers, who would talk about distributed optimization methods and what are the related problems, what are the challenges, and how the proceedings, this special issue covers this topic. And then Professor Mike Rabat from Facebook, who talks about practical aspects and applications um, of these problems. Wahid, over to you now.